Welcome to my presentation. My name is Alexander Marquardt. I am a PhD student at Bonn-Rhein-Sieg University of Applied Sciences and University of Bremen. And I'm presenting my research with the title Comparing Non-Visual and Visual Guidance Methods for Narrow Field of View Augmented Reality Displays. The problem with many current augmented reality devices is that they still suffer from a very limited field of view. Therefore, it can be challenging to locate virtual objects in augmented reality applications. For this purpose, researchers created a variety of visual guidance methods to find virtual objects that are outside the field of view. However, with the use of visual methods, the potential clutter of information, occlusion, and other visual conflicts can occur, especially in very information-rich environments. Non-visual guidance techniques can be used to overcome these restrictions. Furthermore, the question arises, how much the situation awareness of real environment is affected if these guidance techniques are used? In this paper, we address the lack of understanding which technique should be preferred under which usage conditions. The goal of this paper is to compare a state-of-the-art visual guidance technique with an innovative audio-tactile guidance approach. Users have to solve a guided search task with a narrow field of view device under different task load conditions. With regards to this goal, two research questions arise. The first is, how well do non-visual guidance methods perform compared to visual guidance methods for a search task on different levels of task load? The second research question is there an effect of guidance method on situation awareness when a secondary task is included? For this, we created a 2x3 within-subject study where the user has to solve a simple search task to find out-of-view objects continuously. For reasons of comparability and controllability of the conditions, we simulated the augmented reality application in VR. The dependent measures are, firstly, two guidance modes, namely audio-tactile guidance and IC360 as visual guidance method, and secondly, difficulty, respectively, task load divided in three levels: no noise, with noise, and with noise and a secondary task to solve. No noise condition uses a static background as environment for the user without any distractions, which can be seen on the top figure on the right. With noise conditions uses a vivid urban city environment where the user experiences rich optical flow information and auditory noise. This can be seen in the center image. And the last task load condition uses the same environment but with a secondary task to solve. Here, the user has to react to a moving object in the background during the search task, namely a flying bird. This is illustrated on the bottom image on the right side. For the performance measures, we take a look on the hit rate and the search time of the found out-of-view objects. For the situation awareness measures, mainly the performance of the bird detection and the questionnaire ratings were analyzed. I will describe both used guidance techniques now briefly. Audio-tactile guidance uses a headband attached with 5 vibration motors. The motors are placed in 45-degree intervals from -90 to +90 degree on the user's forehead. With a mixture of auditory and tactile cues, it is possible to guide the user on the longitude, latitude, and depth. The longitude will be indicated by the currently vibrating motor position on the tactile headband. When the user turns his head, the vibration wanders with the head rotation until the feedback at the center of the forehead informs the user that the target is located directly in front of the view direction. Also, an interpolation effect is used. When two adjacent motors vibrate at the same time, it indicates that a target lies in between the physical motor setup. For the latitude, an auditory cue is played. This cue adjusts its pitch and volume to the current viewing angle. The highest pitch and volume indicates the correct target latitude. Depth, on the other hand, is indicated by a vibration pulse metaphor, which is inspired by popular parking assisting systems. A pulse describes the on-off pattern of the currently used vibration motor. Very short pulsing indicates that the target object is very close to the user, while a slow pulse is indicating that the target is far away. IC360 is a so-called out-of-view visualization technique. It projects a 2D map on the screen with dots called proxies representing the target objects. It is quite intuitive in usage for longitude and latitude, since you just need to follow the direction of the proxy symbols. Also, the depth is encoded by the color of the proxy symbols. Proxy symbols can take a color of a gradient from red, which means that the target is close, to blue for distance targets. Next, I will show a demonstration of both guidance techniques and how they work. Next, I will report about the performance measures of the user study. Regarding the hit rate, both guidance techniques are comparably high for all task load levels. Only audio-tactile guidance had a significantly higher hit rate for distance-located targets. Regarding the search time, unsurprisingly, IC360 was faster than the audio-tactile mode at each task load level. Only distant targets took significantly longer to find with IC360 compared to finding closer located targets. Regarding the situation awareness measures, we analyzed the secondary task, namely the bird detection task. The users noticed the bird 28% faster with audio-tactile guidance compared to the visual guidance mode. We also counted how often the bird enters the total HMD field of view while the user was solving the search task. Here, using audio-tactile guidance led to less field of view entries until the bird getting noticed. Furthermore, users could detect the bird better with audio-tactile mode, while more birds have been overseen using IC360. Finally, users stated in the questionnaire that they could concentrate better on a secondary task when using audio-tactile guidance. Subjective cognitive workload during the experiment was measured by the NASA Task Load Index. Here we found out that there was an effect of task load on cognitive workload. A lower overall workload level was measured in the condition without noise compared to the condition with noise and noise with secondary task. The affected NASA TLX workload subscales were mental demand, performance, and frustration. Also, there was a marginal effect of guidance mode on the frustration subscale that indicates that users felt a higher frustration using IC360 across all task load conditions. Our conclusion of the result is that the choice of the guidance technique should depend on what you need to solve the task best. If the task requires fast search times, a visual technique like IC360 should be concerned. If situation awareness is of predominant importance, non-visual audio-tactile guidance might be the better choice. Regarding the hit rate, both methods perform similar results, so the guidance mode could be selected by personal preference. Future work includes the extension of the tactile headband with more vibration motors to achieve a higher resolution for receiving tactile information. Furthermore, it would be interesting to investigate a hybrid technique using visual and non-visual guidance information. However, this has to be investigated more thoroughly in order to combine these techniques in an effective and consistent manner. Another important topic is the ability to enable multiple target guidance with audio-tactile mode, since the current system is only able to locate a single target at a time. Finally, the integration of eye tracking would be a promising approach, for example, to improve object selection during the search task. This was a presentation for the paper with the title Comparing Non-Visual and Visual Guidance Methods for Narrow Field of View Augmented Reality Displays. Thank you for listening. I will gladly answer your questions now.